Welcome to a new test and teardown video. This time it's a Wiltron model 350 phase meter, 10Hz-2MHz, and both of the inputs. Look at that, the ranges 1 millivolt to 2 volts. Or 200 millivolts to 400 volts. They can be individually set. The phase meter ranges 5, 10, 18. See, this is a little bit funny at the first little look at it, but of course it's because there is a 180 readout here, and then you have, of course, also the 80. You can offset this, so subtract something and make it 0. And there is a low pass filter, I guess, for the phase output. And you can variable 0 this one. And you can invert, I think one of the inputs, you invert this. And then you can make it 0 again for, correct the readout of something like that, right? So I think this is not of much practical use today, because I think that most modern oscilloscopes like this one should be able to read out the phase much more stable, much more accurate, and all that kind of stuff. I hope to benchmark all this, and let's see and compare if this is really the case. I scored this one a few days ago for a very, very low money, so I'm super happy and excited about it. And I just checked on eBay. There's one for sale, $995 plus shipment. Holy moly. Oh yeah, by the way, look at the knobs. Where have you seen those knobs? This looks like Heathkit. Isn't that fascinating? So of course this is US made. Probably also from the 1970s, 80s, something like that, right? And that is why we have seen exactly this type of knob on Heathkit. So here at the back, we can see it looks so much like Hewlett-Packard as well. Same fuse, same, I mean, everything, the whole feeling and stuff like that. It looks a lot like Hewlett-Packard. We got this sticker here. It says serial number. Ooh, this is a very high serial number. And here we got the Wiltron sticker. All right, let's open and have a look. So let's look a little bit inside this unit. So far, I'm not super surprised. Or maybe I am, because all the circuit boards, they point down. But that is just the way they decided it could be easier or better or something like that. I don't know. Mostly I see components sticking up, but of course. So look at this. This, of course, the voltage regulator. And it's from 1980. So this is the first component I see with a year code. So this is my first guess. Maybe we can find some more information. So where's the circuit board for this or that? I haven't got a big clue yet, because as just looking at the back of the 3 different circuit boards, you don't really see so much what is going on. We see the different filters for the low pass filters for the phase output. That's of course just some capacitors you select in. That will be the different ranges for the readout system. And see, we got some resistors here, and they're using high precision components, so all that is good. See, 0.1%, that is very, very good. And the silver plating of the switch is of course completely black, so I have to clean this a little bit. This is the invert switch. Look how black the silver becomes. See, there's a little shiny stripe, and that is because I've been moving the switch a little bit. Maybe I can clean this a little bit better. Oh yeah, mains power on off switch is here, and look, they put it inside a wall like that, completely sealed and shielded cable and all that kind of stuff. And that is of course because this down here is the input with 1 millivolt sensitivity. So of course you can't have mains going up here with several hundred volts swinging up and down and coupling to everything down here. And also we'll have these capacitors and timing and all that for the 2 inputs. So this is of course the input amplifier, Smith trigger and all that kind of stuff. And it's of course the same for the other channel. And stuff like this is of course very, very sensitive. So it's a good idea to shield everything. We got rectifiers down here, and here we got the voltage selector. Don't you just love this side? Oh, transistors and tons of them. I love it. So that's of course the input, and this switch down here is the selector between the millivolts and the many volts of input range. And of course you got a little capacitor here to compensate for input speed and all that kind of stuff. And that will be the amplifier and Smith triggers and all that kind of good stuff to make this into a good stable signal. And the other board here is exactly the same. Besides, I can see a little bit of repair was done. You can see here there's a transistor, that one. See, and here you go. That one was changed, and it's all just NPN and PNP transistors. Probably they know some of them. They tend to blow up in case you put in too much or in the wrong range or something like that. So this is maybe why they're in a socket. Over here, that will be, of course, the readout board, and some of this over here, that will be the power supply. This power supply is a little bit interesting as well, because we got 2 capacitors here connected to chassis, opposite direction. This reveals we have a positive and a negative supply system, and we have a big capacitor here as well, and a big hefty NPN transistor. So that means we have unsymmetric power usage, because this one is a much more powerful positive supply, and that will be a little equally tiny little plus and negative supply, and probably that will be those 2 transistors if I'm not mistaken. So yeah, that is more or less how it looks. We got the big rectifier diodes and all that is up here mounted on the back. And I don't think this thing uses a lot of power. All those transistors, this is just a few little millivolts per transistor, so it's not a lot. It's also using these beautiful white transistors as well. And sometimes they look like this when they are field effect transistors, but that is not the case with this one. It's just NPN transistors. So oh, there's a little hot resistor. Not too hot, I hope. Yeah, I still haven't found any leaked capacitors, blown up components or anything like that. I think this one passes visual inspection, so that means let's power it up. So let's try the first power up. What I've done here is I got 2 inputs. This is of course sine waves. Those are a little bit difficult to measure compared to using square waves, but let's try with sine waves. So this is a 1 kHz signal, and the phase input is also read out here. It's due to be about 10 point something, and I believe my input is here, 10% here. So I can just dial this one, and I can verify this on my scope, and then the signals goes into my meter here. So at the first power up, I should get -10, +10, depending on how this is set up. Let's put this in here. Let's put this in the middle. I don't know, plus minus degrees, whatever, right? Let's power up input, and it hammers. Oops. Is this normal? Really? So why are you doing this? Is it still warming up? Is this just because all my switches, they are... Look at that. I need to clean everything. What is this measuring? I think it's measuring something really funny, huh? Let's try and remove the input. Aha! So it's this input that makes all the funky. So this is the funky chicken, huh? No. So this one gives us something. The other one gives us nothing. And then both of them gives us... What are you doing to me? Well, let's see if we can find a schematic. Yes. I think I'll start with cleaning all the switches, and then I will see if it's more stable. Probably also the transistors in all the sockets. Let's give them a little bit of a massage and see if there's anything better. But this is not. Let's give it 0 degree input phase like that. Okay, there seems to be some sort of a response. So all I did was a lot of cleaning. All the potentiometers, all the switches, everything I cleaned. And now we are back again. Let's see how nice and stable it really is. That is unbelievable. As you can see here, we have 0 degrees input. So let's see if we can put it down. Okay, so this is 50. Maybe there's something to do with the zeroing. Okay, look at that. So there is some... Why is that? What am I doing wrong here? So this is annoying, this the time constant. So you want this to be fast, right? So here we go. Now it's faster and easier to work with. And then this is doing some... Okay, so here you go. Here you add something, but why can't I get it to the other side? Then it goes all the way around. But why the heck? So let's see. Those two inputs, they should be the same, right? Come on, man. So, this is weird. Why can't I get it the other way? Let's do it like this and then... I don't get it. Give me a minute. So I think the instrument actually works, but I got now 20 degrees input, as you can see here on the scope, and 20 degrees seems to be the zero of this one. I can't really figure out what to do to fix this from the front. So of course we can attack the trimmers and all that on the inside. At least all the switches and potentiometers, see, they are working really good and nice. And everything should of course be in zero. This one should be in zero. This is how you can do this positive or negative, I bet. See, if I put this for 50 degrees, okay? So if I give it 10, see, 10, 20, 30, and then you can negative it, see, again. So that is how this unit works. So I was of course wrong by doing this positive and negative. This is not how it works. The idea is you use this one to make it positive or negative the offset. So let's pretend that I put the input, as you can see here, back to 0. So now we have 0 on the input, so it says 20 here, right? So I want to remove those 20, and I can do that. Now we are back and fine. We have a 0 that is just 20 for whatever reason it is, right? Now I can zoom in to 5 degrees, and there is no way to do this finer on this one. Then I can 0 here. So now I have zeroed the meter because I know the input here is 0. Let's try something funny. Let's try. We have 0, and we are now in the finest readout. So let's swap the two inputs and see if that is exactly the same. And it is, because now I know these two are correct, right? So that means my offset here is wrong, so there's something I need to fix. So let's try and give it 1, 2, 3, 4, 5. And now it reads 4. Let's go the other way. 1, 2, 3, 4, 5. And then it reads 4. So it reads a little bit low. Let's go in the 10. Back to 0. Oh, so in this range, of course, you need to adjust it again. This is all old tech analog, right? So of course we need to recalibrate in each of the ranges. Okay, we can live with that. So let's play again. So this is now 10, and now it reads 9. Okay, let's go the other way. Minus 10. Oops. Here you go. Minus 10, and it reads 9. So it's not super bad, but it's also not super good. This 20 here is a little bit annoying, but I think I will see if I can find some schematics again. I just gave up looking for schematics, but I will try one more go and see if I will be able to do that. Look at that. So this is actually 200 kilohertz input, and no phase difference. Look at that. We're in 0 here, and I have the capability to hit 0 adjust within this range, and I am in the finest. Look at that. And it's still nice and stable. It reads out a little bit less the higher frequency. So let's try again. So this is 1, 2, 3, 4, 5 degrees. And then you see it's still 4 that it reads out, right? Let's go the other way around. Yeah, and it's again 5, and it reads out 4. So let's try and change the frequency again to 1 kilohertz, and the other input is also 1 kilohertz. And here we go with the input. And then all I have to do is put it into 0 again. And now it works. So what have I done to get this result. Yeah, I was just poking around with the trimmers more or less random, not completely random. I'm not a super dummy, but of course the two amplifiers, so all the potentiometers in the two amplifiers, what they're doing, they will of course amplify, and there will be some Smith trigger, and there will be a trigger point auto zero thingy, obviously, because it can do a very wide input here, so there will be a clipper and a limiter and all that kind of stuff. So that will move the phase a tiny little bit when you poke around with the trimmers in the two amplifier section. But over here, the phase detector, those trimmers in the middle of the picture right here, those are the ones you poke around with to get the zero within this knob's working range. So I think I'm more or less done with this unit. All I now need is something I can use it for. Of course, I have a modern scope that can do all these things. I can do I don't know, many screens of all sorts of analyze this versus that. You can even put in your own parameters, your own settings, your own math, your own whatever you want to do, all right? So there's maybe not so much to use a phase meter for today, but let's see. Please come with some practical experiments or something that I can use this for. The first thing I was thinking about, that was like stepper motors, resolvers, all those things with some angles and different frequencies, and then it should of course show us how many degrees per step and so on. So that this could of course be interesting. Other than that, I can't really come up with anything to use it for. Anyway, I look so much forward to see your comments on practical use. So see you around. I hope you had a little bit of fun. Bye bye.